Good to go.
All right, let's get going. All right, well, good afternoon, everybody. It is my pleasure to introduce to you today Chelsea Snide. Chelsea graduated in 2019 from the Department of Atmospheric and Environmental Sciences at the University of Albany, where she did some undergraduate research with alum from this department, Andrea Lang. After she finished her degree, she went on to do grad school at the University of Michigan under my supervision. And after about a year, the whole group moved to the University of Wisconsin here, where she continued to do research here and has completed her master's thesis. Now, if I had to describe Chelsea in a few words, I would say that she's very hardworking and has a strong sense of diligence and responsibility. And you'll see the results of that today. As a testament of Chelsea's ability and commitment to her research, she essentially did all of her master's research in less than 1 year. Essentially, all the research got done in the fall semester, and these results were essentially put together into a manuscript and then submitted to publication in the spring semester. And that's going to be the topic of today's talk. The paper is currently now under revisions. That was submitted recently to the Journal of Climate. And as you'll see today, it is excellent. It's an excellent piece of work, and I hope you all like it as much as I do and the rest of our group does. So without any further ado, Chelsea, take it away.
Hi, thank you for the really great introduction. As Angel mentioned, I'll be talking about the paper that we submitted in for review, and my topic is titled "The Role of the Large-Scale Moistening by Adiabatic Lifting in the Madden-Julian Oscillation Convective Onset." And as you all know, my advisors, Dr. Angel Adames, and my two committee members are Drs. Larissa Beck and Angela Rao. So to kind of give a quick introduction of what the Madden-Julian Oscillation is, I will be referring to it as the MJO. So what the MJO is that it's a convective envelope that spans thousands of kilometers. So to give you an idea of how large this convective area is, it's about the size of the United States. So associated with this convection is also an overturning circulation, which you can see on the figure provided by NOAA. In the lower levels, you can see that winds are converging over the Indian Ocean, where the Madden-Julian Oscillation often initiates. And this convergence is forcing upward vertical motion associated with convection and divergence aloft. And this overturning circulation has an end branch eastward of the convection, which causes anomalous, dry anomalies forced by the downward vertical motions. And that associates circulation. And this entire circulation of the MJO is about half the width of the planet. So this is a very significant and very large circulation, and it's one of the most important modes for intraseasonal variability. So to give an idea of how the MJO cycle works, this figure is taken from the Madden and Julian paper from 1972, and these columns show time progressing. So time, as you go down, time is going forward, and it continues on to the second column. So to give an idea, generally we see the MJO initiate over the Indian Ocean. So this is around 60 to 100 degrees longitude. And again, we see the upward vertical motion associated with the convective updrafts, as well as that overturning circulation. As time moves forward, we can see this convection starts to grow stronger as there's more moisture fed into the convection. And we see that the MJO propagates eastward very slowly at about 5 meters per second. And it continues to grow strong. If we hop onto the second panel, we see that the MJO starts reaching the Western Pacific Ocean around longitude 180 degrees, and the convection starts to weaken. And the convection primarily weakens due to the cooler sea surface temperatures over the Western Pacific, But as we keep going down in time, we see that although the convection starts to die off, this overturning circulation associated with it continues to propagate eastward a bit faster at about 30 meters per second. And this circulation sometimes continues on back into the Indian Ocean to then create another active MJO over the Indian Ocean. So this circulation is really important to the climate system, as you can see by just how large scale it is, but also its circumnavigating feature. And it profoundly impacts the global circulation. So if we look at this figure that I've provided on the left from the UCAR Comet program from Adiabatic et al. 2014, we can see that each of these blue dots on the graph represents a location where there's a statistical significance for precipitation teleconnections associated with the MJO. As you can see, these blue dots are widely spread out, both impacting the mid-latitudes and the tropics and all the continents. We can also see that there's these little hurricane symbols as well. And these are places where there's statistical significance for teleconnections with tropical cyclone genesis associated with the Madden-Julian Oscillation. And lastly, we can see that the convection and the associated circulation causes changes in the general atmospheric flow, which is represented by the different highs and lows pressures that you can see both in the upper atmosphere and in the lower atmosphere. So as you can see, the MJO widely impacts the globe, both locally in the tropics, as well as through teleconnections in the mid-latitudes. And this is very important for what's called subseasonal to seasonal predictability, which is the time frame between 2 weeks to 2 months. And this is really important for emergency managers and the energy industry as well as the agriculture industry. So it's really important to understand how the MJO works and how it's represented in our models. So one of the biggest outstanding issues in simulating the Madden-Julian Oscillation in the global circulation models is our understanding of MJO convective initiation. And models generally do this very poorly, and that's not too helpful for forecasting and predictability. So if we look at this figure below provided from the DOE, we see that prior to initiation, or the pre-onset, that we have moistening at the surface, as well as shallow to no clouds over the Indian Ocean, allowing for there to be a lot of surface heating. This surface heating, in turn, is going to allow for convective updrafts and diabatic forced vertical motion, which is going to help create the transition of shallow clouds to deep tropical convection over the Western Indian Ocean, which is what we define as initiation. So once the MJO initiates, we get these really large and deep tropical clouds. And this is often associated with the strengthening of the circulation, so we get anomalous low-level winds as well. So to look at MJO initiation from a different perspective, I've provided 2 phase space diagrams. And to just get everybody acquainted to how to read a phase space diagram, the MJO can be broken up into 8 phases. And on this lower panel map are the different phase numbers, which represent different locations around the equator. So, for example, phases 2 and 3 of the MJO represent locations in the Indian Ocean, 4 and 5, the maritime continent, 6 and 7, the Western Pacific, and 8 and 1 represent the Western Hemisphere and Africa. So if we look at the first phase space on the left-hand side, this is for primary events. We have our phases 1 and 2 associated with the quadrant that's labeled A, 3 and 4 with the quadrant labeled B, 5 and 6 with C, and 7 and 8 with D. And you can also notice on the phase space diagram that there's two circles. The first solid circle is the circle of unity. So this represents an amplitude, so a measure of how strong the MJO is. And the dashed line is what we will be using in the study, but I'll talk about that later, but it's an amplitude of 0.8. So when the MJO is in the circle, that means there's no prior MJO activity. So to give a little bit more of a definition of what a primary event is versus what a successive event is, if we look at first at the primary events on the left, we see that day 0, which is their first day of initiation, is the larger white circle, which starts at phase 2. If we go back in time following the blue dots, we see that prior to initiation, there's no MJO activity. And this is what makes a primary event what it is. So it's one that initiates with no previous MJO activity. This contrasts the successive events fairly well. So if we look again, we see the white circle and represents lag day 0, which is initiation. If we go back in time looking at the blue circles, we see that instead of no activity, that the MJO is fairly strong in quadrant D and starts decaying in quadrant C. So this is what we call the circumnavigating signal, which just means that this is the circulation from a previous MJO that circles back into the Indian Ocean to then create another convective onset. So a lot of theories have been proposed for both the primary and successive events, and here are some of the more recent and popular ones. So for primary events, there's a few. There's the nonlinear moisture advection, moistening by cumulus convection, and there's also theories regarding triggers from extratropical influences and equatorial waves. Looking at the successive events initiation theories, there's two leading theories for how these events initiate. So the first one is the large-scale horizontal advection hypothesis. And this is just explaining how prior to initiation, we generally see a pre-moistening signal in the Indian Ocean, which is caused by the horizontal advection of moisture from the maritime continent going westward into the Indian Ocean. And secondly, we have the free tropospheric moistening by the anomalous dry adiabatic lifting hypothesis. And this just deals with the hypothesis that small temperature fluctuations in the tropics modulates convection for initiation. So here we go into a little bit more of the theory of these MJO studies. So many of these previous studies pertaining to the MJO assume that there's weak temperature gradient approximation, which I'll shorten to WTG. And what WTG approximation is the balance between diabatic heating and the vertical advection of dry static energy. So to give a more clear idea, we can look at the thermodynamic equation, which is listed here, where our first term is our time evolution of temperature. Then we have our vertical advection of dry static energy term, and that's equal to Q, which is our diabatic heating. If we assume a scaling for the large-scale tropical atmosphere, this is how our terms scale. So we see that our temperature evolution term is a magnitude smaller than the other terms. So this is what we consider the primary balance, and this is what many of the previous studies assume, which is not a bad assumption as shown by the scale analysis. However, in this study, we're proposing to use a relaxed weak temperature gradient approximation. And with this approximation, we again can look at the thermodynamic equation, which is listed on the left-hand side of the screen. And instead of neglecting these temperature tendencies, which are small compared to the other two terms, we can expand out the equation. So if we can replace omega and expand it out into two components, an omega q, which represents the diabatic vertical motions, and omega a, which represents the adiabatic motions. If we sub this equation into the thermodynamic equation, we can come up with two different balances. So as I talked about previously, we have our leading order balance, which is the traditional weak temperature gradient approximation, where the vertical advection of dry static energy by diabatic heating diabatic motions is exactly equal to diabatic heating. But then we also get a second order equation, which shows that the temperature evolution or these small temperature fluctuations are balanced by the adiabatic, the vertical advection of dry static energy by adiabatic motions. And although these vertical motions are a lot smaller than diabatic motions, about one scale order smaller, we hypothesize, and it's been shown in observations, that it does play an important role in the evolution of convection. So in our study, we decide to not neglect the temperature tendencies. So to give a little bit more of a further view into this, we apply our relaxed WTG approximation to the moisture equation, which shows the different processes and terms leading to moisture evolution. And if, again, we scale this equation based on the large scale tropics, we can see that each of these terms are the same magnitude. So our first term is our moisture tendency, followed by our large scale horizontal moisture advection. And then we have the vertical moisture advection by adiabatic motions, followed by the vertical moist static energy advection by diabatic motions, the radiative heating, which is QR, and then our turbulent fluxes, which include our surface fluxes as well. And one important thing to note here is that even though we saw that the adiabatic motions are small and negligible or can be neglected in the thermodynamic equation leading to traditional WTG, the adiabatic motions cannot be neglected in the moisture equation as shown by our scaling. We see that adiabatic processes are on the same scale order as our diabatic processes. And this is primarily because the diabatic processes lose a lot of moisture from condensation. So even though adiabatic motions are small, we don't get this loss from condensation. So these terms end up being of equal level of importance.
Hey,
so based on
Larissa had raised her hand. You had a question.
Oh, sorry.
I just have a quick question. Why are the adiabatic motions advecting moisture while the diabatic motions are advecting moist static energy, right?
Yeah, so I didn't show like the whole derivation here, but if we expand out like I did here with the omega, this is what we get. I guess I can show you maybe afterwards the full derivation.
Okay, that's fine.
I just, for simplicity, omitted it.
Yeah, I can probably find it too. I was just curious if there was a simple explanation for why one of them is advecting moisture and the other is advecting moist static energy. But, okay, thanks.
Yeah, no problem. So to move on, this has led us to ask the following questions for this thesis work. So the first one being, what are the predominant thermodynamic processes behind the Madden-Julian Oscillation convective initiation over the Indian Ocean? And then what role do the adiabatic motions play in both the primary and successive MJO events? And on the basis of this relaxed weak temperature gradient approximation, we hypothesize that the vertical moisture advection from the dry adiabatic descent plays an important role in the MJO initiation events, as shown in the scale analysis from the previous slide. So just to give an idea of what data we're using, so for our composite analysis of primary and successive events, we're using the ECMWF ERA-Interim reanalysis. And this is 32 years spanning from 1979 to 2010. And it's on a 1.5 degree horizontal grid. Secondly, we're sourcing outgoing long wave radiation or OLR data. And this is from the NOAA polar orbiting satellites. And this is on a 2.5 degree grid. So with the variables we're calculating, everything that's going to be shown is going to be anomalies that are created using the full climatology and then pass through a 20 to 100 day land coast filter to retain MJO signals. Just to make sure everybody's acquainted with the area of interest, the first square is the larger red one, and that's our domain. That's our Indian Ocean domain that we're going to be averaging over and are interested in. And this is 10 north to 10 south latitude from 60 to 100 degrees east longitude. You can also see that there's a smaller pink square, and this represents our DYNAMO domain, which is roughly 3 degrees north to 3 degrees south from 70 to 75 degrees east. And I'll talk a little bit more about DYNAMO in the later slides. So to get more in depth on how we identify the initiation events, I have the phase space from earlier in the introduction. And our primary and successive events are determined based on the methodology found in Matthews 2008. But instead of the RMM index, we use the OMI index, which is the projection of the filtered OLR onto spatial EOFs. So we chose to use the OMI index primarily because we're interested in the convective initiation, and because OLR is a good proxy for convection, we decided to base our analysis on this. So to get a little bit more in depth with how these are identified, again, as we know from primary events, those are events that initiate without any MJO activity prior to them. So everything in this in the dashed circle has is represented by a letter N, and that just means no MJO activity. And then for initiations over the Indian Ocean, we know that phase 2 is in the Western Indian Ocean. So we're looking at when the first active day is in quadrant A. So to give an example, the primary events will have a sequence of N, so no activity followed by a pattern of A, B, C, D. So no activity followed by a full cycle of the MJO. Likewise, with our successive events, we know that these events initiate from the circumnavigating signal. So we're looking for an active MJO signal prior to initiation. So we're looking for the sequence D, A, B, C, D. And we find 23 events for primary and 50 events for successive. And to just give a bit of a basis, the amplitude is determined based on OMI 1 squared plus OMI 2 squared and taking the square root of that. And we chose to use a threshold of 0.8, primarily so we could include, have a wider selection of events than what an amplitude of 1 would give us. And it's important to note that in the Matthews 2008 study, they use a threshold of 0.4 for activity. And we just wanted to be a little bit more conservative with our threshold than their study. So again, just to look at the moisture budget again, because we are going to be looking at plots of each of these terms. All these plots will be a column integration. So again, we just have our moisture evolution, horizontal moisture advection, the vertical moisture advection by adiabatic motions, which I'll just refer to as adiabatic processes, the vertical moistatic energy advection by diabatic motions, which I'll just refer to as diabatic processes, the radiative heating, and then our surface fluxes, LE and H, are going to be looked at as together. So you will be looking at the sum of the surface fluxes instead of individually. So to kind of dive into the results a little bit, to make sure that the categorization of primary and successive events worked well, we wanted to check and see the evolution of the composited primary events versus the successive events. So what you're looking at right now is a plot of primary events, and in the shading are OLR anomalies, and in the contours are chi anomalies at 150 hectopascals. And just for reference, chi is the velocity potential, and you can think about this as something that represents large-scale divergence or convergence in the atmosphere. So this is a measure of the circulation associated with the MJO rather than the convection. So to start off, we can see in the primary events at about lag day -15, we have a positive OLR anomaly, which is this purple blob over about longitude 70 degrees. And we see that this positive anomaly doesn't have any really clear eastward progression, and is then followed by a negative OLR anomaly by lag day 0, which is our initiation. We can see as the negative OLR anomaly propagates eastward that it also strengthens as well over the Indian Ocean, and the convection eventually decays at about 180 degrees, lining up with the Western Pacific. Likewise, we can see that this negative OLR anomaly is associated with a negative chi anomaly, which again is in the contours, and we can reach this chi signal all the way back to about lag day, maybe -10, over South America, which is at around 300 degrees longitude. And this has been shown in previous studies on primary events from Roundy and Cicada, who showed that there's a signal originating from South America that comes into the Indian Ocean during primary events. So we see here that there's really no clear previous MJO events, so we can be confident that our composite are actually primary events. We can then look at the successive events on the right-hand side, and in contrast, we can see that there's a circumnavigating signal in the chi and OLR that reaches back to about lag day -35. So we see a negative OLR anomalies begin over the Indian Ocean around 60 to 100 degrees longitude and start propagating eastward alongside a negative chi anomaly that continues through the Western Pacific, the Western Hemisphere, and then comes back into the Indian Ocean at about lag day 0, where it then initiates another event. And likewise to the primary events, as the MJO progresses, it starts to strengthen in the OLR anomaly, signifying that the convection is also strengthening. And we see a similar decay as it reaches the Western Pacific. One thing to note with the successive events is that the OLR anomaly can be found going back to Africa, and so we can see that the successive events clearly have a circumnavigating signal, and we can also see them in the OLR wave train. So we have the negative OLR anomalies over the Indian Ocean starting at lag day -30. We are progressing through time going down. So at about -10 lag days, we have the positive OLR anomaly. And then again, during our initiation period at lag day 0, we again see a negative OLR anomaly, which is consistent with what was found in Matthews 2008. So we can also look at initiation through the decomposition of omega Q and omega A. So first, we're looking at the primary events. On top, you can see in shading is omega Q, and the omega Q and omega A are going to be column averages and not integrals. And this is contoured with OLR. So that's just a typo, but you can see that omega Q is closely follows the progression of the OLR anomalies as they move eastward and are pretty contained to that region. You don't see the diabatic motions going any west of the Indian Ocean. And we can see a similar pattern in the screen below, which shows omega A in shading and the chi anomalies again in the contours. We see that unlike the diabatic motions, the adiabatic motions are not necessarily confined to convection and closely follow the chi anomalies. We see that the adiabatic motions can't really be traced back into Africa, but appear over South America. And it's one thing to point out, there's a ton of noise between like that 0 to maybe 20 longitude line. And this area right here is Eastern Africa. And it's a very mountainous region. So we're getting a lot of noise from over here.
Can I just jump in with a clarifying question?
Yep.
One of those you said is the velocity potential and one of them is the adiabatic motion. Is that right?
Yep. So the bottom panel in the shading is the adiabatic motions, which are column average, and in the contours are chi, which we saw previously.
Okay, thank you.
Yep. So likewise, we can do the same thing with our successive events. Omega Q is in the top panel, and that's in shading. And we can see, unlike in the primary events, the OLR anomalies and the omega Q anomalies can reach back over into Africa at around longitude 0. This is reminiscent of the circumnavigating signal. We can see the similar thing happening with the adiabatic motions in the bottom panel, where they again closely follow the velocity potential, but there's a more clear signal through Eastern Africa as well as through the Western Pacific and going back in time to the Indian Ocean. So we see from these two plots that very clearly the primary and successive events have some clear characteristics. So kind of moving on to our results in the moisture budget terms. So to just give an easier picture of what these look like, we average them over the Indian Ocean, which again is from 10 north to 10 south, 60 to 100 degrees longitude. And we're looking at primary events first. So to get you acquainted with the graph, it goes from lag day -15 from the left, where lag day 0 is in the middle, all the way to lag day +15 on the right. So what we have plotted here are all of our terms, and in black is our moisture anomalies, which are Q. And to kind of start off to see what happens prior to convective initiation, to no surprise, we see the horizontal advection term is positive and contributing to the moisture evolution prior to lag day 0. As soon as the MJO starts initiating at lag day 0, which corresponds to the maximum in the moisture evolution, which is not shown, we see the horizontal advection then becomes negative. We see a similar trend with the diabatic motions as well, although a bit smaller, which is in red. Moving on to the adiabatic term, which is the blue line shown here, we see that prior to initiation, it's weakly negative, but as soon as it gets to lag day 0, it becomes pretty positive and about the same magnitude as the horizontal advection term is, and it peaks at about lag day 8, which is the same time the moisture peaks as well. And we can see the similar pattern with the radiative heating, which is the orange line, where it peaks slightly after the Q, the maximum in Q, but they're wildly in phase. So these two terms, this suggests that these two terms are important to the moisture maintenance of these MJO anomalies. So we can look at the same thing again for successive with the same coloring scale. At first glance, we can see that both primary and successive events follow a similar evolution, where we have horizontal advection becoming a maximum at about lag day -5 prior to initiation, although this advection term is a lot stronger than they are in primary events, and this is hypothesized to be because of the circumnavigating signal. We can also see with the diabatic processes, which are in red, that they're a lot stronger prior to initiation due to the suppressed phases of the MJO. And as soon as it initiates, both of these terms become negative. And here the diabatic term largely tries to dry out the MJO through the condensational processes. Looking at the adiabatic terms in blue again, we see a similar thing as in primary. We have negative all the way up until lag day 0, where it becomes, where it strengthens and becomes a maximum at about lag day 8. But one big difference between the successive and primary events is the strength of the adiabatic term is about 50% stronger in successive events than they are in primary events. And there's a little bit of a different phasing between the maximum and the moisture anomalies and the maximum in the adiabatic motions. So we can estimate the contributions of each of these processes to MJO initiation by performing projections. So on the top shows both primary events. So in the blue bars is the contributions to moisture evolution, and the purple bars represent the contribution to moisture anomaly maintenance. So if we first look at the contribution to evolution, again, to no surprise, we see that advection is one of the leading terms for moisture evolution, with the second largest term being the adiabatic. We can also see that QR also leads to evolution, and that diabatic is one of the largest negative terms. It's important to note out that this last bar here is a residual, which is extremely large, especially compared to horizontal vertical advection, but we'll talk more about this residual later. Looking at the maintenance, we see that the tendency is positive, which is the first bar, meaning that the MJO is strengthening. We see that the two largest terms contributing to the maintenance of anomalies are the adiabatic term and QR. We see that advection and diabatic heating contribute negatively, and in both cases of evolution and maintenance, the surface fluxes are negligible. We can see the same thing for successive events, although the magnitudes are a lot stronger. So in the evolution, we see advection is the largest contributor and it is larger than the residual here. And we also see, again, that adiabatic processes is the second leading term. But a big difference between the two is the QR contribution. So in primary, it's positive, and in successive, it's negative. And we hypothesize this might have to do with the shape of the convection. Looking into the anomaly maintenance, as we expected from the line graphs, we expected the adiabatic and radiative heating to contribute positively to the moisture maintenance in successive. And we can see that these are both larger magnitude than they are in the primary, but also the diabatic term is largely negative as well. So we see that the diabatic and adiabatic processes in both are roughly of equal magnitude and are trying to cancel each other out. So to kind of deal with our residual, which is primarily due to model increments and just general mathematical error due to like the model increments as well as the parameterizations, we wanted to include the events in the DYNAMO field campaign. And based on our criteria and categorization, the 3 events that were captured in DYNAMO are considered successive. So this is more comparable to our successive events from ERA-Interim. And these figures for DYNAMO are credited to Victor Maika, who's our postdoc in our group. So to kind of walk you through this figure, Again, we have the same coloring scale for the line graph on the bottom plot from -15 to +15 lag. And then on top, in the blue and black, are cues, and this is just two different data sources for the moisture anomalies. So we can see that the DYNAMO soundings primarily follow a similar evolution from ERA-Interim, where we see this diabatic term, the horizontal advection term, again, which is in green, positive prior to initiation, as well as the diabatic term in red. As soon as the MJO initiates at day 0, we have the positive adiabatic term and positive QR, but we also have surface fluxes, which play a pretty large role, which are comparable to the adiabatic motions. And these surface fluxes were negligible in our ERA-Interim data. One thing to note is the scaling here is a lot different from our ERA-Interim plots, and a lot of this can be explained due to our domain averaging. So if we make our domain smaller and closer to where DYNAMO was, we see that our magnitudes get a little larger. So a lot of that is contributed to our area. But another thing to note is that even though the scaling is different, our adiabatic term in both DYNAMO and ERA-Interim scales to the same level of magnitude as the moisture evolution term. So in both of these, adiabatic processes are important. We do the same thing with the projections. Again, these figures are provided by Victor. We have the contributions to moisture evolution on the left and the maintenance on the right. To walk you through it real quick, again, to no surprise, advection is positive, contributing positively to the moisture evolution. But one big difference is our diabatic term, which is the second bar, is actually playing a positive role in DYNAMO, where it played a negative role in ERA-Interim. We also see our adiabatic motions are a lot smaller and play a negative role in the evolution, where we saw them play a positive role in ERA-Interim. But we have drastically reduced our residual, which is the last bar on this plot. Maybe something that's a lot more similar to our ERA-Interim analysis is the contribution to moisture maintenance, where we have the tendency on the first bar, and it's important to note that this is negative, whereas in ERA-Interim it was positive, but this is largely due to the domain, which we tested, and then we do see in agreement with ERA-Interim data that adiabatic motions and the radiative heating do play a positive role in anomaly maintenance. We also see surface fluxes play a positive role, where they were negligible in ERA-Interim, and again, a small residual. So just to quickly kind of compare the two results, they qualitatively agree with each other. Although the processes in DYNAMO are about a magnitude larger than in ERA-Interim, but that can be explained by the domain averaging. We also see that adiabatic processes are the same magnitude as the moisture tendency in both data sets, signifying that adiabatic processes cannot be neglected. And we see that surface fluxes play a large role in the DYNAMO, but are negligible in the ERA-Interim analysis. So to kind of put all this together, Angel has created a schematic kind of explaining the evolution of MJO initiation. So going from lag day -15 to +15, we see that prior to initiation over the Indian Ocean, the atmosphere is dry and we get a lot of warming from diabatic processes. We see that there's suppressed anomaly convections from downward vertical motions in omega Q, which is the red line. And as we move forward, we see that as we get closer to initiation at about lag day -5, that our horizontal moisture advection plays a role, which is represented by the U wind in black. As the initiation starts to occur at around lag day 0, we see the transition from shallow convection to deep tropical convection. And we see that we have upward vertical motions in both the adiabatic and in diabatic motions. And we know from this analysis that our adiabatic motions and those processes are contributing to moitness and anomaly maintenance in the MJO, while omega Q and the diabatic processes are contributing to drying just due to the condensational loss. So to put this all together, we see that the large-scale horizontal advection plays a critical role in the pre-moistening of the free troposphere for both primary and successive events. We see that the vertical moisture advection by the adiabatic lifting is of leading order importance for anomaly maintenance for both primary and successive events. And these results indicate that the small departures from WTG balance play an important role in the developing stages of the Madden-Julian Oscillation. We can also expand the study a little further, and some future work might include performing model intervention experiments to test the degree to which the dry adiabatic lifting plays a role in MJO predictability. And this can help us understand how the forecast changes based on how adiabatic motions are represented, and can help improve predictability. And of more like personal interest, we can also do the same analysis and quantify how these vertical moisture advection by dry adiabatic motions are represented in the subseasonal to seasonal prediction project database. And by doing a comparison of the numerous models, we can shed light on how MJO prediction can be improved during the crucial initiation stages. And lastly, I just want to acknowledge everyone who has helped me. So as Angel mentioned in the beginning, most of this research is from a submitted journal article. So I want to acknowledge my co-authors, who are Drs. Angel Dames, Scott Powell, and Victor Maika, for all of their help and their insights. And also just, I want to thank my advisor, Angel, because he's been honestly really supportive, as well as with the rest of his research group, which includes Rosa, HC, and Kayleen, and Victor. I've learned a lot from them, and I'm glad I was able to be a part of this group and explore both like my academic interests as well as I guess some of my other personal hobbies. And I also just want to acknowledge some of the friends who've been really helpful during my graduate school experience and who I've learned a lot from. And those are Ingshao, Chloe, Sakina, Posh, and Karimar. So thank you.
All right, Chelsea, thank you so much for your talk. I'm going to open up now the session for questions and see if anybody has any questions.
I have a question. This is Greg Tripoli. Have you, and by the way, that was a very, very nice talk. I enjoyed it.
Thank
you. I have a question though. I find in tropical cyclones particularly that one of the key ways the atmosphere is prepared for upward motion is through the saturation or the moistening due to virga or rain that may or may not reach the ground, but on the way down, it moistens the atmosphere. What that does is it raises the saturation point and cools the temperature that allows more heat to be picked up by the ocean surface, and together they're able to raise the equivalent potential temperature to the values that are necessary for upward motion to reach the high tropopause as they do in the tropics. So this type of moistening by precipitation, I think, is quite important, and I would guess that it rivals the effects of adiabatic lifting in terms of moistening the deep atmosphere. Have you looked into that?
We haven't looked into that specifically, just because we were, I guess for the study, focused more so on the larger scale dynamics. But I think that would be something interesting to consider. But I do still think that the adiabatic motions are important for kind of counteracting the condensational processes as well. And maybe the moistening by precipitation just adds more to the moistening. but I don't think that's a reason to be neglected. Maybe Angel might have something to say since his mic is going off.
Yeah. So Greg, that's a great question. And like Chelsea said, we haven't looked at it. We can't quantify it. Like it would be, you can take the diabatic term, the vertical moistatic energy advection by convection, and decompose it into different terms, in which like a Virga term would be incorporated in there. The only downside is that in reanalysis, we don't have the data to do this analysis. I think it might be possible to do it with sounding, or more, even better still, probably using like a small scale model analysis, like running a WAR for cloud resolving model. I think we can probably quantify that. So it'll be an interesting question for future research for sure.
Thank you.
Larissa's got a question. Go ahead, Larissa.
Yeah, I'm just wondering, I'm kind of trying to wrap my brain around physically how I should interpret this adiabatic lifting. Are these circumnavigating Kelvin waves? Like what kind of processes do you think are forcing this adiabatic lifting? Are we thinking
That's a
like huge equation? Like what are
Yeah, no, that's a really great question. Angel and I have discussed this a little bit, but for the study, we didn't really delve into what is causing these adiabatic motions. I guess the study was more focused on the diagnostic aspect of whether or not these motions play a role or not, but we hypothesized that a lot of this probably has to do with the Kelvin waves, but it needs to be tested.
So you're thinking like the circumnavigating Kelvin waves, like kind of the MJO, or this, I guess I'm just asking you to speculate. I'm not asking for you to necessarily have an analysis that proves the answer.
Yeah, no.
Your best guess, it sounds like, would be that it's the MJO turning into a circumnavigating Kelvin wave, not having a convective signal for a while and then becoming convective again. Is that?
Yeah, that's exactly what the thought was.
Okay.
Can I ask a random question as an oceanographer with my just random things coming into my head, Chelsea? I was wondering, given that your secondary events are described as the MJO kind of completely circumnavigating the globe and coming back around and having fairly strong signals at like negative lag days, for example, is it possible that some primary events are secondary events, but you have sort of destructive interference in your signal depending on like which phase of the wave arrives at that point? If that makes sense, or does it matter at all? I was wondering if anybody had even looked at something like that.
So are you referring to, sorry, do you mind just repeating?
Yeah, so I'm referring to like your figures in the kind of in the beginning. Yeah, so where you have these propagating, a little further down. No, not those. Where you've got your propagating, yeah, like this one versus your primary versus your successive one. So if you notice, like in your successive figure, you've got like, you know, negative or positive OLR anomalies at like lag day -10. And then not and weakly positive ones at lag day -10 in the primary events. Can you get something weakly positive if you have like a strong negative signal that's actually interfering with that? Like that's what I'm wondering is like, can you actually have something that propagates all the way around that cancels that out and makes it look like there is no MJO there, but there actually is? It is totally okay if you don't know. I'm really just curious, and I was just thinking. So I know this is like a weird question. Larissa's looking at me like I'm nuts, so apparently no.
Yeah, I'm not exactly sure how to answer it, but these are all filtered for the MJO signal from 20 to 100 days. So I suspect most of the signal probably can be attributed just to the MJO.
Mm-hmm. Okay, sounds good. Thank you.
I think, Larissa, did you have another question?
Yeah, I had another question. I'm still kind of trying to wrap my brain around what these adiabatic motions are. And you had mentioned they're connected to velocity potential. Is there a reason why the adiabatic motions are connected to velocity potential, but the diabatic motions wouldn't be? Or
Yes.
just kind of trying to wrap my brain around how to think
Yeah.
about the adiabatic motions.
So to just kind of go back to the decomposition of these two, so omega q, which are the diabatic motions, can just be thought of as motions associated with convection, which is why we primarily see them contained to the OLR anomalies, which we use as a proxy for convection. But our adiabatic motions are more associated with the circumnavigating signal, which is represented by velocity potential. So these adiabatic motions come about due to small temperature fluctuations associated maybe with the wave, whereas the diabatic motions are just associated with diabatic heating, which we've seen in tropical convection.
So, but the
If that clears-
diabatic would be associated with velocity potential variations too, right? The velocity potential is just telling you about where there's vertical motion. Am I missing something? I guess it's more spread out in the bottom panel than in the top panel, but
Yeah,
I guess
just
clear sky motions versus motions within conduction. Like I understand the diabatic balance. I'm just trying to, yeah, maybe we should talk more offline, I guess. Or maybe I should talk to Anhel, both of you maybe together.
Yeah, definitely.
Yeah, so just to add to that, like you're right, like there's no reason, like the diabatic, the omega q's should follow the velocity potential as well. I suspect that what is going on, and of course I didn't, this has just been in my head and I haven't talked about this to anybody, but I suspect that what happens is that the adiabatic lifting is actually weight number 1. So when you calculate the velocity potential, it actually contributes to a big fraction of the velocity potential calculation. Whereas I think the diabatic motions, since they're confined to the worm pool, they tend to be of slightly higher weight numbers. So, so for just like, just because the adiabatic motion field is kind of preferentially favoring the largest zonal weight number, that it tends to align well with the velocity potential. I think that's really the only reason why that happens.
Thank you.
And to add to that, like, that's just kind of like a hypothesis. Like we haven't really tested or proven that in any way or form. It's just, it kind of just makes sense, but like we should, it's definitely something that needs to be proven.
Sure. So you're thinking sort of the planetary scale MJO signal is associated with these adiabatic motions, but then the diabatic motions are confined to the worm pool in Indian Ocean. So those are higher wave number for that reason.
Yeah.
Yeah. So that I guess kind of also relates to your theory of the MJO, but yeah.
Yeah, that's right.
Well, I'd love to chat more about that.
Yeah. Does anybody else have any questions? Okay, well, I see we're at the time. So thank you, Chelsea, for your time, and thanks everybody for attending. I hope you all have a great afternoon, and we'll see each other, I guess, in the next seminar or something like that.
So Anhel, are we